So I will continue to discuss the other problems, and you should, this sample test version 1, sample findings version 1, and you should really spend time to work on sample finding exam version 2, and I will come here Friday, okay? And you can ask me any questions from the textbook or from sample test, sample finding exam version 2, okay? Well, those are not the problems you should focus on. You should, if you feel difficult to do some problems, and go to that section and work on the rest of the problems, similar problems, okay? So you cannot just say, oh, I understand that particular, then I'm okay. If I change the problem, are you able to do it? Okay. So there'll be about 14 problems. So that 2 hours. It's about the same time per problem. Okay. So the next problem I want to discuss is about the following one. We using a divergence theorem to evaluate this surface integral. Now, when you see, sometimes I will tell you use a divergence theorem to evaluate the surface integral. If I do not mention that, and you see as this is a surface integral over a closed surface, then you have an option whether you can use a divergence theorem to evaluate the integral, or you just parameterize the surface and evaluate it as a surface integral, convert it to a double integral instead of a triple integral. Okay, there are two options to do this problem. Okay, and here let's see, this is solid bounded by the cylinder. Now this cylinder, this is a surface, so it's not closely connected. Something wrong with my connection here. Oops. I cannot touch it carefully. All right, so with a cylinder, and here's x squared plus y squared equals 1. Let me finish writing the problem. And the planes equals x plus 1 and c equals 0. Okay, so you look at this problem. All right, so step 1, you really should, if possible, sketch the graph. Just rough idea, that helps you to solve the problem. If you, this is cylinder, right? Z equals 0 is the xy plane, and the x plus 1. In order to sketch that graph, all you needed to do is look at the 3 intersection points. The plane Z equals x plus 1. So when no restriction on y variable, right? That was a z equals x plus 1. The slope is 1 in the xz plane, and the yz intercept is 1. It looks like that. Okay, this is a plane. So how do you draw it? It's hard. You extend this side, and so this line is the xz plane, and so the cross section looks like that. Okay, so this is a piece of solid. okay, in the XY space. All right, so if you want to treat it like regular surface integral, then how many pieces here? The surface, 3 pieces, disk, and the top, right? And then the cylinder, portion of cylinder. It's very hard to evaluate the surface integral over 3 different surfaces. It takes about 1 hour to finish that. All right, so you have to, even do not mention divergence theorem, then you, as long as it's closed. Now, sometimes even not closed, you make it closed. Why? Because, like say, if I say the bottom part is not included, then what do you do? Of course, you cannot use a divergence theorem, but you can also add the integral on the bottom part, okay, and then make a closed surface. But that part, addition part, probably is trivial integral, okay. So if you look at the solutions to sample test. I remember I posted. Yeah, I gave another solution. I know I add. For example, you have 3 surfaces as 2 surfaces, the top and the side, cylinder, and without the bottom part, I just add the bottom part, and total together should be converted to a triple integral, and then evaluate that triple integral. Then you have to subtract the integral, surface integral on the disk. And then maybe that is 0 even. Okay, so anyway, this is so by the divergence theorem, this will be the triple integral, right? Partial derivative of x squared with respect to x is 2x, and that is 1, that is 1. All right, so you will be surprised. That would be that would be x plus 1. Now x plus 1 is not going to be 1, right? Even it's not going to be it's not even going to be z, because only on this top part, okay, and x plus 1 is z, okay. So the next what you're going to do is, this is triple integral. You should convert it to a double integral, and then one single iterative integral. So this disk is d. D is going to be x squared plus y squared less than 1. So for every point, okay, for every point x with coordinate x and y, you draw a vertical line, right? Then so the solid is filled with those vertical line segments, and now you evaluate the integral along this line segment. So z is the lower bound for the z is 0. The upper bound for the z is x plus 1. Okay, x plus 1 and dz. Okay. Then you get the x plus 1 is constant with respect to z, so just x plus 1, and then h is squared here, dA. Okay. The next part is to use a polar coordinate that's from 0 to 2 pi, and from 0 to 2 1, and x is r cosine theta plus 1 square, and d, and there's r here, don't forget r, and the dr d theta, okay? And then you open it, right? So it's gonna be r, so I get r square, r cubed right now, and plus 2r square cosine theta plus r, because there was r here, bounded by r. So dr d theta, this is a square, okay? So you can evaluate with respect to r first, then you get a quarter cosine square theta plus 2/3 cosine theta and plus 1/2, because r, the antiderivative is r squared divided by 2. Okay, so d theta, and this is clearly going to be 0. The integral cosine theta from 0 to 2 pi 0, and the cosine square theta is going to be half of 1 plus cosine 2 theta. So the integral, it is going to be a quarter and times 1/2, then 2 pi. And here's 0 as 1/2 is 2 pi. Okay. So finally you get what is that? You get pi over 4 and pi, so pi over 5, right? So pi plus pi over 4, pi over 5, is 10 over 4, yeah, 5 over 2. All right. Yeah, the most important part is always all the way to here. Okay, I only give 2 points to the remaining computation. Okay, I want to see how do you change it to the double triple integral and how to change it to the iterative integrals. The remaining part is just just evaluate the integral using polar coordinates. Okay. Now, what happens if I do not include the bottom part, right? So what is the surface integral? Yeah, of d and over the d, and this is the s ds. Okay, look at this. This is the surface integral at the bottom. Okay, if the surface integral at the bottom, right, this is d in the x y plane. Okay, so at the bottom, and the normal vector is pointed to the other side because if we want to make a closed surface, right? I just just double integral. View this disk as a surface in the space, right? This is a true problem, right? How do you evaluate? Okay, and oriented pointed downward, right? So for this surface integral, how do you evaluate, right? And because over this surface, okay, if f is going to be on the disk, f is going to be just x squared I plus y j, right? And the z is going to be 0 actually now. Yeah, z is going to be 0, right? Right? Because then the normal vector is going to be k, negative k. And then the ds is actually dA, okay? This is just flat, okay? dA, yeah, ds. Actually, ds here is just dA, ds just dx, dy, okay? It's true. So, but when you multiply this out, you see that's going to be 0 dA, right? And that's going to be 0. So that part, even the bottom part is not included, if I said it. And it does not make any sense, any difference, okay? So if I ask you, if I make the problem a little bit complicated, I just say, hey, this is surface does not include the disk, right? And then evaluate the surface integral. What you're going to do is you add the integral at the bottom part, right, over the surface at the bottom part, and that's 0 actually. When add 0 to it, then you get a closed surface, and then you can use apply the divergence theorem to solve the problem. Okay. All right. So the next problem is find the area of the surface. Okay, z equals xy. All right, so this is a graph actually. Now, I wish you to treat like a surface as integral of the integral constant 1 over the surface. Okay. So this is again the cylinder. Cylinder is the easy case, right? So cylinder and z equals xy, and remember zx xy as a product could be negative. Okay, it depends. So some surface inside, it's hard to draw it. Okay, it's actually can be negative, can be below the axis, can be above, can below the xy plane, can be above xy plane, because x times y when it's negative, it's z is negative. So that will be surfaces under the xy plane. Okay. Now, I really want you to understand this as a surface, as the area of the surface is coming from this, the integral of ds. Okay. If we consider that, then for the graph, ds is going to be dx is going to be, you know, square root of 1 alpha x squared plus f fy sub y squared. Okay. The reason is you parameterize this. Okay, and then as the ds is, you know, ds is nothing but this is given by this. That's the reason the cross product gives that. The reason I want to do that is because sometimes the graph is not given like a z equals x times y. It could be y equals x times z, you know, something like that. Okay. All right. So the next step is just to evaluate this the square root, okay, of the function. So x, the partial derivative of f with respect to x is going to be y, and that is going to be x squared plus 1 and dx. Okay. So how do you evaluate this integral? That's polar coordinates. Okay. So here is going to be r squared plus 1. This on the d theta. This is a very simple integral, and let's use a substitution. Okay. So if you use first of all, let's take 2 pi out. Okay. Just focus on this. And then let u to be r squared plus 1 and du equals 2r dr. Then u is from 1 to 2 and u to the 1/2. And this is r here, right? Yes. Oops. Did I touch it? Okay. This will be half of du. Then the antiderivative 2 cancel out, be pi, and the 2 over 3, u to 3 over 2. All right, but we do need to know this the formula, the parameterization. Yeah, using parameterization to find the ds. Okay, for example, if I ask you to find the area okay. Okay, find the area of the surface. Okay, and this time I use or set up integral. Maybe I'm not able to evaluate integral. Okay, so I will use y equals x squared plus, let's just see, okay? And so this is going to be x is between 0 and 1. Z is also, yeah, z is between 0 and 2, okay? Just a square rectangle. So when you see this is it's a graph, but it's not like a usual graph z equals f of xy, okay? So either if you consider this one as a function of xz, then the area of the surface, you can write down this directly, but this times fx squared plus fz squared plus 1, and then dA. dA here is dx dz instead of dx dy, okay? So then it's going to be here, it's going to be 2x squared, and that is 1 squared plus 1. So dA, okay? So here it's hard, yeah, it's hard. So it's a square. So integral from 0 to 1, x is right, it's dx. Z is from 0 to 2, and dz. And here's 4x squared plus 2, okay? Okay, so if we exchange, so it's constant, it's independent of z, so you get 2 squared 4x squared plus 2 dx. The question is how to evaluate this integral. This is a problem from Math 166, okay? So when you see x squared plus 1, right, you can take 4 out to become 4 here, to x squared plus 1/2, okay? So the standard substitution is going to be x equals square 1/2 tangent theta, okay? And then you can evaluate. Yeah, look at this, x squared plus 1/2 dx, right? Find the antiderivative of that. So it's going to be it's 1/2, so square 1/2 taken out. The tangent square plus 1 is going to be secant square theta. But the derivative of tangent, yes, equals 1 plus tangent square theta is going to be secant square theta, okay? And there's a derivative of tangent theta. I forgot that, okay? But you can easily use find the formula. It's I think it's no, yeah, that's right. So you just find the derivative of tangent theta, right? So still the denominator is the denominator. Actually, it's a secant square theta too, right? Okay, it's going to be yeah. So the denominator is cosine square theta. Numerator is sine. So sine becomes cosine. Then minus, so become positive. So it's actually going to be 1 over cosine square theta. So it's a secant square theta. So you end up with some integral. Okay. The problem is how to evaluate. You can, okay. Yeah, I should just continue. It's a 1 over cosine cube. Cosine cube theta, d theta. So my idea is I multiply cosine theta, numerator denominator model, so it become cosine square theta. Then cosine theta is going to be coming from the derivative sine theta. So you get, and this you will get, yeah, if you let u to be sine theta, this will be du. And the cosine 4 is going to be 1 minus u square n square. I think it's a very complicated problem, but so you can evaluate it. You can evaluate, okay? You can find it, and it uses several substitutions on the way. Why you can evaluate this one? It's called, this is a polynomial, and you can decompose it to the sum of part fractions. Okay. So I stop here. I'm not going to waste time to evaluate this input because this is a randomly picked up problem. We're not, if we have to ask you to, if I have to put a problem like that, you have to carefully choose the functions. Right? Make sure you don't need to waste time to evaluate the integral. Now, but the graph is not necessary to be, the surface is not necessary to be the graph. Sometimes you do need to find the ds, okay, using parameterization for the surface, okay, and yeah, such like a sphere, for example, right? Sphere, for the whole sphere, you can have a single parameterizations, okay, and you cannot view it like an upper hemisphere, lower hemisphere. You can view it as a graph of functions. Yeah, let me give you a problem. Evaluate the surface integral of the sphere. I have to put S is the sphere, x squared plus y squared plus z squared equals 1. Right. And if I put a constant here, I get an area. Now, if I put a z here, you get 0 because z can be negative, positive, cancel out, right? So what I'm going to do is I'm going to put a z squared here, okay? ds. Okay. Now for this problem, it's not a graph. You can view it as a graph, right? There are a couple ways to do. The sphere can be decomposed to two surfaces, okay? Upper hemisphere, lower hemisphere, and z squared is symmetric about z-axis. So you just need to evaluate the integral of the upper hemisphere and multiply by 2, okay? So what I'm going to do here is not going to view the surface as a graph of function, okay? Instead, I'm going to parameterize the sphere, okay? So you can get x equals sine phi, yeah, sine phi cosine theta, y equals sine phi sine theta, z equals cosine phi, and phi is between 0 and the pi, and theta is between 0 and the 2 pi. It's a sphere coordinate, but the radius is fixed, right? And this is a picture here, the sphere, right? For every point on the sphere, this is a phi, and projection here is a theta, okay? So every point was called in the x, y, z can be expressed in terms of phi and the theta, x squared plus y squared plus z squared, okay? Now, if you memorize this, if you memorize the cross product of of the two derivatives, okay, and where x, y is given, then you can save your time. Otherwise, you have to do the computation. It's going to be sine and it becomes cosine phi, cosine theta, cosine phi, sine theta, negative sine phi. Okay, the other one is going to be negative sine phi, sine theta, sine phi, cosine theta, and 0. Okay, and to save time, you just put Ij here, so in order to get the cross product, right? So the cross product, it is going to be, what is I? I is cross product of this. It's right. It's going to be negative sine square phi cosine theta. Okay, that's I. Yeah, the cross product, right? This cross product, right? No, it's positive, yeah. Okay. Then the next one is and here will be negative sine square theta and sine theta. Okay, J plus sine phi cosine phi x sine phi cosine phi and the k. Okay, so you get actually you get the cross product. Okay, so the cross product, if you take sine phi out, what do you see? You will see that sine phi cosine theta I plus sine phi sine theta j plus cosine phi k. So this is nothing but the position of that particular point. Actually, if you want to, yeah, this is nothing but the x, y, z. Right? This is actually the vector itself. Okay. All right. Anyway, so ds is going to be the norm of this, right? And dA is d phi d theta, right? In the using. So this is nothing but sine phi, and the length of the eye is going to be 1. Okay. So the cross product is not going to be does not have unit length. Actually, the length of the cross product is sine phi. Okay. So now the surface integral s. Okay. So the surface integral z squared ds becomes, okay, the double integral. What happens? Okay, the double integral phi is between 0 and pi theta is between 0 and 2 pi, okay? The double integral of z square, z, remember, what is z? What is the expression for the z? Cosine phi. Okay? And the ds is sine phi, and the dA. And the, okay, so this is independent of theta. When you integrate it, okay, and you will get, I think a 2 pi can take it out. They're just integral of sine phi, right? This is a d phi d theta, okay? Sine phi d phi, okay? So use a substitution. Let u to be cosine phi. You will get integral du equals negative sine phi d phi. So you get when cosine phi 0, that's 1 pi negative 1, and the negative u square du. Okay. you can change the order of the interval, and you get 2 pi 1/3 uq from negative to positive. Okay, so the top is going to be, you're going to get 4 pi. Okay, because of 2. 1 minus -1 is going to be 2, so it's 4 pi. So 4 pi over 3. We spent so much time finally get this. So the integral can be evaluated, right? But if I put z squared there, I think there was a trick to solve the problem, because the sphere is around the sphere. Okay? In my opinion, the integral, the surface integral of x squared ds is going to surface integral of y squared ds is the surface integral of z squared ds. Do you agree? Yeah, because they are x, y, they are in equal position, almost by the symmetry of the sphere. Okay, that's great. So that means they're all equal, right? So it means z squared ds is going to be 1/3 of okay. Yeah. So that means it's 1/3 of the surface integral of x squared plus y squared plus z squared ds. But over the sphere, x squared plus y squared plus z squared is going to be 1. Right? Which is going to be the area of the sphere, but we already know the area of the sphere. How do you get that? We still use this sphere coordinates, okay? And that is going to be area of the sphere is 4 pi r squared. That's why I still get 4 pi over here, okay? But how do I know the formula for the area of the sphere? You know, if you forget it, you still have to evaluate this integral. Okay. Nothing is stable here. Right. Almost it's the last review class. I'm not going to use this class now. Oh. All right. Let fxy to be 2, 1 plus y, x squared plus y squared. Right? Find the local, let's simply call the extreme values, maximum, minimum values, and set points. So that was a long time ago we learned, right? Of the function. Okay. So we have to find this. First, find the critical numbers. Okay. Right. Those are the only candidates gives you the extreme local minimum value, extreme local maximum, local minimum value. So you have to find the critical values, critical points. Critical points are determined by those equations because the function is differentiable. By definition, critical points where either the derivative function exists, then must be 0. Otherwise, the derivative function does not exist. Okay, there are two options. It could be very sharp vertex, and where the function doesn't have a derivative, but still the function can have a local maximum, local minimum point, such like that. I know I don't have the specific function for you. This is local maximum point, but the derivative does not exist. Okay, those are do not exist. Okay, because like this place, it's a local maximum point and there must be 0, the partial derivative. The reason is, if you want to find the tangent plane must be horizontal. The tangent plane horizontal if only if the partial derivative is 0. Okay, there are two possible cases. So the both are called the critical points, the corresponding point. Okay, so the function is differentiable. The graph is small. So the first picture never shows up. Okay, but in some cases, yes, you need to be careful. Yeah, don't forget the point where the derivative doesn't exist. Okay. All right. So let's find out partial derivatives. Right. Let's get 2x. So it's going to be 4 1 plus y x fy. Fy is a little bit complicated. And the first factor is 2x squared and 2y, I think, right? Okay, so the derivative okay, you have to set this to be 0, and we have to solve it. From the first equation, you will see that x is 0 or y is a -1. Okay, if x is 0, y must be 0. Okay, from the second equation. Okay, so from the first equation, y equals -1. If y equals -1, and then what is x? Because x squared is going to be -1, right? So it's x squared is going to be +1. +1, so x is going to be ±1. So you have 3 points here. Okay, 3 points. But now, it's not like in one-dimension case. You can check the behavior, local behavior of the function by the sign of the derivative, where the graph is increasing or whether the graph is decreasing. But here the surface, how can you say decreasing, increasing? No way. Okay, right? And it's harder to tell. You cannot describe as a function of 2 variables. In 2 variables, say this is increasing function. Increasing is only one direction. But now the surface is defined on the domain, all directions there, right? And so you don't know which way it's increasing. So we cannot use it. So we use a similar theorem called the second derivative test. Remember in Math 165, you learn the second derivative test. With the second derivative test, the second derivative at the critical point is positive, then it's local, positive, then it's local minimum point. Negative is local maximum point. Okay, and then we remember that. So let's recall recall some results in Math 165. So if the derivative is 0, right? And then you remember if this is a positive local maximum, local minimum. So don't confuse. Positive means positive. Okay, because it looks like a parabola. You compare with the function. If you forgot the relation between the sign and the local behavior of the function, just look at the y equals x squared. Okay, y equals squared, the second derivative is positive. Okay, and then if the second derivative is negative, it implies local maximum. Okay, so local maximum. So that's the relationship. Okay, the y the example is y equals -x squared. Okay, concavity. Okay, so for in 2-dimensional case, right? In 2-dimensional case, you get partial derivatives. Okay, actually you get the matrix. Okay, in 2-dimensional cases, if z equals fxy, okay, And we also assume that we assume that f sub. So we get some point critical, right? And it's called critical point. So the question is whether the function is positive, if the function has a local maximum or local minimum. So the idea is you look at the matrix, the second derivative here form matrix instead of just one single function, okay? Second derivative will be like this. Okay, I'm going to those who took Math 171 should be easier to understand the matrix. This is 2 by 2 matrix, okay? 2 by 2 matrix, that's called M. Okay, so if M is positive, okay, that means local minimum value, okay? So local minimum. So f of, the function has a local minimum value, at that point, more particular, right? And if M is negative, matrix negative means negative definite, okay? But there's a way from a linear algebra how to determine whether the matrix is negative, okay? So local maximum value at, I just want you to compare this result with the one you learned in the second derivative test in calculus. This is second derivative test, okay? Okay, compare with the one in one variable, okay? So how do you determine a matrix is positive definite? Positive definite, here positive definite really means the matrix, okay? It's like that UV times matrix, and UV is positive definite for any UV not equal to 0, okay? That's the notation, okay? But how do you check whether this is always true? It depends on the eigenvalues. If the eigenvalues positive, both are positive, then this is positive definite, okay? So we call it lambda 1, lambda 2 positive, okay? Yeah, so those are the eigenvalues. I assume that you only took Math 171, okay? So now, if you have a matrix using A and the B and the C, okay? Suppose like that, right? There was 4 components. How do you know this eigenvalue is a positive definite? At least the determinant, at least A is positive, plus the matrix AC, the determinant. The determinant is AC minus B squared, as this is a positive, okay? Yeah, it's the same as, those two equivalent. That's coming from the linear algebra. Otherwise, you confuse why you have to look at the first component and then look at the first one and then also the determinant. Determinant itself, the positive does not guarantee a lambda 1, lambda 2 positive. Only guarantee the product lambda 1, lambda 2 positive. Those are two equivalent, okay? Because the determinant is going to be the product to eigenvalues from linear algebra. Okay? And so if lambda 1, lambda 2 are both negative, the determinant is still positive, okay? So that was when the matrix is negative definite really means this product is going to be negative definite, okay? And it's the same as lambda 1 is negative, lambda 2 is negative, okay? And how do you determine that? Look at the coefficients here, and that means A is negative, but the determinant should be also negative, positive. So that's the reason why it should be positive, because if lambda 1, lambda 2 are both negative, it's guaranteed the product is positive, okay? That's the reason. This still keeps the same. So what happens when lambda 1, lambda 2 have an opposite sign? All you needed to do is just look at the determinant, okay? So lambda 1, lambda 2 have an opposite sign if and only if the product is negative. If only if AC minus B squared is negative. So some lambda 1, lambda 2 have an opposite sign if and only if the product is negative. If and only if AC minus B squared is negative, okay? Right, then this will be, in this case, you get the set point. Y, okay, set point looks like that. One side and the other side going like that. Okay, so you can sit on that. Okay, yeah, it's harder to draw, but this is set point. The reason is it depends on sign. In this case, along this line, lambda 1 is positive, other lines lambda 1 is negative, lambda 2 is negative. So it's the two curves, you can describe those two curves. Okay, so this is a good idea. Now we go back to our matrix. Okay, we already have so many points get 0, 0. Okay, we have to find the second derivative. Okay, let me copy the function f sub y is, yeah, it's gonna be 1 plus y x. I think it's 2, right? Or 4. Okay, the second one is 2. Right. So we got critical point, which is 0, 0, and when y is -1, x is positive. No, it's opposite direction. When x is positive 1, y is -1. When x is negative, y is also negative. Oops. Okay, so we are going to have those points. Okay, those are the points. You double check that this is a x. Yes. Okay, so we have to find the derivative, the second order derivative. Fxy is going to be fyx. Doesn't matter which one you use, and that is going to be 4x. Okay, then fyy is going to be 2. All right, so we have to evaluate this matrix. Yeah, let me denote this matrix 4, 1 plus y, and 4x, 4x. Oops, 4x, 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 it's 2, okay? So we want to see whether it's positive or not. So when at 0, 0, right? Yeah, let's x equals 0, y equals 0. The matrix is going to be 4, 0, 0, 2, clearly positive definite, okay? Yeah, both eigenvalues, both are positive. And when x, okay, sorry. Then what you can say, f00 is a local minimum value, okay? Jump to the conclusion. When x equals 1, y equals -1, let's see, when y equals -1, this is going to be 0, 1, 4, 4, 2. Now what? Okay, and this one, clearly the determinant is going to be negative, okay? So it's good determinant, okay, which is 0 times 2 minus 4 times 4 is going to be negative, okay? So that means 1, -1 is a set point. Okay. No, it's not local maximum value. The function doesn't have a local maximum, doesn't have a local minimum value. Okay, and the problem is similarly. When x equals -1, y equals -1, because you get a 0, right? When y is negative, that's a 0, but this is a -4, -4, and 2, but does not make any difference. Okay, so the determinant of this matrix is going to be still -16. It's negative. So 1, a -1, 1, -1 is a center point. Okay. So this idea can be generalized to functions in more than 2 variables. Could be a multiple of 7 variables, 6 variables, 1 million variables, and you want to find local maximum value. And the computer can do the computing very fast, 1 million variables, no problem. Okay. Yeah, we are going to learn more mathematical ideas to deal with the problems come from application other areas of science. All right, so now the problem. Given the point, has coordinates 1, pi over 3, -3. In cylindrical coordinates, okay, change from cylindrical to strict coordinates. Okay, so we have to understand how do we get the cylindrical coordinates in the space, right? And we use a cylinder to describe. Actually, we use a polar coordinate. Okay, an arbitrary point, x and y, z, right? And you describe it using the polar coordinates in some sense. So we project this point to the xy plane. Yeah, if we forgot what is the sphere coordinates, that's how do we get it, right? So x will be, and this is x will be just describe x, right? X will be r here. The cylinder has radius r, right? R cosine theta, right? And the y equals r sine theta. Essentially, it's polar coordinates. Nothing changes to the z. Right? For the same picture, right? Now use a sphere to describe a point in the xy plane. The sphere has a radius rho. So the spherical coordinates x is going to be rho sine phi, because this will be r. We project it to the xy plane, this will be r. R is going to be rho sine phi, okay, that's angle phi. Then cosine theta, and y equals r sine theta, and z equals rho cosine phi. Okay, so you have that's a straight coordinate. You have 3 variables: rho, phi, and the theta. I'm pretty sure this is the order. Okay, and how about here? What is the order here? The order here, I think it's r theta z. Okay, make sure what is the first component in tradition. Double check that. Okay, that's what I'm pretty sure. So rho, phi, and the theta. Yeah, 1080. I want to double check, what is their order when describe the point. Well, it does not say that. It's, oh, rho theta phi. You see, that's what I have to double check. That's on my memory. Yeah. So theta would be first. Right? Yes. It's a 1086 page, 1086, 1087. Yeah, okay. So that's the correct order. Now, now how do we do this problem, right? So we are given r theta z. This is 1 pi over 3 and the square of 3. Okay. So z is going to be negative square of 3. Okay. So actually, what you should do is just change it to the x variable. Okay. So change it for the same point. Now, if you look at the picture, r is rho sine phi. Okay. So you have to determine what is this is r, right? Okay. This is r. So theta is already given, the same theta, clearly. Look at, compare these two pictures, right? Theta is the same theta. So clearly but we don't know the rho yet, right? We don't know the rho, we don't know, yeah. So you can write down this first. It's going to be 1, right? And sorry, x. Let's compute x. So x is going to be r times cosine pi over 3. Y equals r times sine. Yeah, sine pi over 3. You don't need to evaluate it because z equals negative square of 3. Okay. For the same x, y, z, you just do the comparison, compare with that, right? So you are going to get, you're going to get the same result. So you do the comparison, you find out rho sine phi should be equal to 1. Okay, rho cosine phi should be equal to square root of 3. That's it. And the theta is going to be pi over 3. Yeah, compare both sides, Yeah, because this is going to be supposed to be rho sine phi cosine theta. That's a rho sine phi sine theta, right? That's supposed to be rho cosine phi. Okay. So then from here, what you can get is rho square, add them together is going to be 1 square plus negative square 3 square, which is going to be 4. Okay, rho is going to be 2. So once you get that, then you have sine phi equals 1/2, cosine phi equals negative square 2. But the phi is between 0 and the pi, so you can quickly determine the phi. Phi is going to be pi minus pi over 6, which is 5 pi over 6. So my answer right now to the problem is rho theta phi is going to be, rho is going to be 2, and the theta is power 3, it's not changed. Phi is going to be that. Just compare those two coordinates, then you can tell you can determine all the angles quickly. Okay. Yeah, this is the first part. Okay, that's it. So what I suggest to you, I already completed the first sample test, okay? And you should do, before Friday, complete the sample test number 2 by yourself. And you do actual homework problem, and bring your question to the classroom. I'm going to answer some of the questions. I'm not going to discuss all the problems, okay? And those who are online watch it, you can also submit your problems during the class, or you can give to me before the class, okay? So I can also discuss them in the class, okay? That's a Friday. No class on next Monday. It's a final exam day, okay? Final exam week. Then Wednesday, but I still go back to my office if you have questions. Also double check all the quizzes recorded, okay? Make sure the quiz, okay. I'm confused. The file is already gone. Probably nobody here. Oops. Was not recorded. Okay, the rest of them. I'm okay. All right. So it was gone.